things you've learned before, but just a reminder that when you multiply and you have the same base, that you add those exponents. This is like a reason why you don't have to write these if you want, but look at this fancy thing I did. So if you want to see like an example, like if you add 2 squared times 2 to the third, it's really like you have 2 2's and 3 2's, which make 5 2's. That's why the rule works. You don't have to write that if you don't want. I was doing this at home on my dinosaur laptop, and it wouldn't let me type exponents, so I had to like copy and paste things from Google, and that's why. And then I did this fancy little disappearing trick. I should just do that all the time with all my examples. I type out all of it and then just click as I go. That would take a while. Now, when you divide, if they have the same base, you can like cross out what they have in common, but the shortcut is you can just subtract the exponents. And again, an example with some 2's here. If you have 2 to the third over 2 squared, it's really like 3 2's over 2 2's, and you can cancel them out. A power to a power. If you have something raised to a power and then another power on the outside, that's when you multiply. And again, I think it makes more sense if you actually write it out. If you have 2 squared to the third, that's not even right. Right? Like, that's not right. That should say like this. It should say 2's. Right? I didn't write that. I stole it from Google. That should be a 2, right? And that should be... Look at that. Look what happens when I try to be cutesy. Should just hand it off. At least I caught it, right? Because that means 2 squared 3 times. There should be 6 2's. Negative exponents, probably people, besides not knowing when to add and when to multiply exponents, people struggle with negative exponents, but remember a negative exponent just means the reciprocal. I always teach my ECA lab, the negative is the ticket to cross the fraction bar. Just turn in your ticket to go to the party. If you don't have a negative, you don't get to move. That's the rule. Let's see what it says here. Probably something incorrect. No, that's right. So 2 to the negative 1 does not mean negative 2. It means 1/2. It's reciprocal. This is a definition, it says. And then this one is the silliest one. It tries to explain to you why anything to the 0 power is 1. And basically, it has to be 1 so that these other rules work. I don't write this whole paragraph down, but where's it at? And it just says, like, if this is true, you have to show that when you have something to the 0 power that it doesn't change anything. So that's their little explanation of why that works. I think it's kind of silly. Hopefully you have memories of this. The majority of your homework today is simplifying problems, not this simple, but a whole bunch of stuff with exponents. So probably like using all these properties at once in one problem. That's exciting, right? There's 2 other properties that I didn't put on this one, but I think I put it on the next page. So if we're good to go, I can move on. What time did we get out of here today? Prime time, 10:30. Okay, I'm going. Yes? Oh no, I just went straight to it. Okay, let's just go. I haven't had to hit this one yet, so. And it doesn't overheat. There's no chance of overheating because there's no projector. But yes, I feel like I'm not very good with this one. Simplifying these. What does simplify mean? It means combine all terms that can be combined together. It means don't leave negative exponents. Put everything together that you can. So these are like my 3 easy examples maybe. And then we'll do some uglier examples with fractions and stuff. But on number 1 there, just remember that you can multiply. We talked about yesterday the commutative property, the associative property. You can multiply in any order that you want. So we just do that without thinking. We group the numbers together, we group the x's together, we group the y's together. And when you multiply with the same base, remember you just add those exponents. So 3 times 4 would just be 12. And then if I have x squared and x, then that means I have, you say? X to the third, because remember there's a 1 right there. Not right there. And if I have y to the fourth times y to the fifth, that is y to the ninth. That is simplified because I can't put anything else together. What about the second one and the third one? Remember that if you have multiplication or division all to a power on the outside, you have to give that power to everything. So this 4 has to go to everything in there. And people do really well at giving it to the variables, but they usually forget to give it to the number. But that would become 2 to the 4th. We'll actually put that on in a second. And remember, what do we do when we have a power to a power? We multiply, so that would become a to the 8th, b to the 12th, and then c to the 4th, because it's just 1 times 4. Don't leave 2 to the 4th, right? Like, you can work that out. It's not 8, it's 2 times 2 times 2 times 2, which would be 16, a to the 8th, b to the 12th, c to the 4th. Questions about that? So number 3 is kind of just like that, except for it has some negative exponents. I'm going to do the same thing first, gives that negative to everything. So that would be negative 2 times negative 3 is positive 6. And b to the third to the negative 3, 3 times negative 3 is negative 9. And remember that we don't leave negative exponents in our answer. It's just not simplified. So if it has a negative exponent, then you move it to the denominator of the fraction. If it's negative in the denominator, then you move it to the top and you drop the negative. So u to the 6 does not have a negative, so it's going to stay on top, and v to the 9th would go to the bottom. One's a u, one's a v. They're not the same, so you can't subtract those exponents because they're not the same base. Questions about that? Hopefully some memories of that. Let's look at some more exciting ones. Maybe I should have switched those because 4 looks a little uglier than 5. That's okay. On number 4, what's the first thing we should do? Look in the back of the book. Yeah, that anytime you have parentheses with an exponent out there before you start moving stuff around, I think the smart thing to do is put that exponent all in there, and then we can talk about moving stuff around if we want. So again, just like on the multiplication, this negative 2 has to go to everything, including that 3. So I'm going to multiply the exponent. So negative 3 times negative 2 would be x to the positive 6. I'm just going to write that as 3 to the negative 2 right now. And negative 1 times negative 2 is positive 2. Anyone have a question on where I'm getting that from? Those are all different, x, y, and 3, so we can't put anything together here, but what we can do is deal with that negative exponent. So since it has a negative, where does it have to go? To the top, right? That's where the whole ticket concept makes sense. It has a ticket, it gets to move up. So I'm going to move that to the top, and I'm just going to write that as 9 if you're okay with that, because that would become 3 squared on the top. And 3 squared is 9. And that looks so much nicer than all those negative exponents. Questions about this? Are you feeling like, oh my gosh, this is a college class? Or are you like, oh my gosh, I'm going to fail class right now? Put your thumb. What should we do on this one? Add these two together on top? Can we add these two together on top? No, because why? They're not the same. One's an X and one's a Y, right? X's and Y's. Can't mix them. So you have two options here, all right? One option is when you have stuff in the top and stuff in the denominator, that are the same base, the rule is you just subtract them. The other option is you could move that negative to the bottom first if you want and then combine stuff. Doesn't matter as long as you're doing it correctly. But remember, you can only put things together if they're the same base. So if I did x to the fifth and x to the third separately, like forget about the y's for a second, I could just subtract 5 minus 3. That would be x squared. And watch your negative signs on this. If you subtract these, you would get negative 2 minus 1, which is actually negative 3, right? Yes? No. Do I leave my answer like that? No, I have to move my negative to the bottom. Simplifying exponents. The other thing that we're going to talk about today is simplifying radicals. We're actually not doing this whole section because it also gets into rational exponents. The thing you're going to see about this college algebra is really like algebra 2. But think about, you took algebra 2 from August to May last year, and we're taking college algebra from August to December. So we're going to have a lot more stuff jam-packed in one section. We meet more often than they meet at Ivy Tech, so we get to go slower than that you would actually have to do at Ivy Tech. They only meet like 2 or 3 times a week, depending on what you sign up for. But they really meet for 3 hours a week. And so we can go a little bit slower, but we're going to go a lot faster than you did in algebra 2 because we're going to cover almost everything you did in algebra 2. We're going to cover in this one semester. So make sure that you stay caught up. See me if you need help. We'll start nice here, and then we'll get ugly in a minute. So remember that if you have something to a power, you can always take the nth root of that. And really, probably before algebra 2, you didn't really do a whole lot other than square roots. But last year, you should have done like cube roots and fourth roots and fifth roots and simplified all of those. And the same rules apply. It just means if you have a cube root, you're looking for perfect cube numbers. If you have a fifth root, you're looking for perfect numbers to the fifth power to do that. So I thought we'd start with some really nice ones that work out really well. And then the ones you're going to see on the homework are not ones that work out well. They're going to be ones that aren't perfect roots that you're going to have to just take out what you can and simplify what's left. Which again, you've been doing with square roots for a long time, but you haven't been doing with higher powers there. So on number 6 there, this one they throw a plus or minus in front of it, which just means if there's a plus or minus in front of it, you're just going to bring that down. If there's not a plus or minus, you just do what's there, whether it's the positive or the negative root. But these are just square roots, right? Square root is when there's no number there. We just know there's a 2 there. And what is the square root of 16? 4. How do we take the square root of variables? Remember? Or what is the square root of x to the 6th? Do you know the answer to that? How'd you get that? It's like there's a 2 out there, right? So kind of the shortcut is if that divides in evenly, you can just take 6 divided by 2 and get 3. Why does that work? Because a square root and a square cancel each other out. So anytime you have an x squared under a square root, you're going to just get x back. Right? Do you agree with that? So it's kind of like saying how many x squareds are in x to the 6th. Well, you could write that as x squared, x squared, x squared. There's 3 of them. Right? That's kind of the reasoning behind it. The shortcut is, if it works out perfectly, you just divide it out, and then you get x to the 3rd. So that's square roots, but all of the roots are in here. It can happen with anything. So fifth roots, you have to think about things to the 5th power. So first of all, 243, it is a perfect number to the 5th power, but you probably don't know it off the top of your head. Maybe a good button to learn on your calculator is that you have an nth root button. On my calculators, it's right below pi, like right where that caret sign is, that you can put anything to a power. And you have to hit, like if you were using your calculator, you have on my calculators, you have to hit 5 first, and then you have to hit that button which looks like this, the X root, and then you would type 243 in, and it would tell you. Or you could just guess and check numbers to the 5th power. So you guess right? You used that button before? Hopefully. It's just 3. It works out nicely. For 5th roots, instead of talking about x squared, giving you the solution there, on a 5th root, do you agree that it's x to the 5th that you want? Like that's what would cancel out? The inverse of the 5th root would be the 5th power, or the inverse of the 5th power would be the 5th root. So again, kind of using Chase's shortcut's great. If you know that, you're just saying how many x to the 5ths are in, or a to the 5ths are in a to the 10th, or what is 10 divided by 5? 2, because you could write a to the 5th twice from a to the 10th. And how many could we get out of b to the 15th? 3. Yes? The thing is, what happens if it doesn't work out nicely? What if it's b to the 16th and the 5th root? You have to think about what's left under the radical, what can you take out of the radical. And again, square roots, you've been simplifying numbers under square roots for a long time, but letters and with higher roots, maybe I think last year, Algebra 2 was the first time that you did that. So let's look at a few uglier ones, and then I think that's it. Start here. So I think good advice is make sure you look at what root you're dealing with first. The big mistake I think people make is you automatically jump to square roots, which you don't want on this one because it's a 4th root. And then think about what you want, right? And maybe we can come up with a shortcut way on these as well. But if this is a 4th root, it would be really nice if there were things that were multiples of 4, because that means it would work out perfectly, but 6 and 3 are not. But if I had the 4th root of x to the 4th, do you agree that that would give me x every time? So, how many times can I take 4 out of 6? Just once, yes? And I'm going to show a lot of work on this one, and then we can talk about whether you want to show that every time. But technically, could I rewrite x to the 6th as x to the 4th with 2 x's left over? Is that the same as x to the 6th? Just like when we do like the square root of 20, you can break that up as like 4 times 5, and then you can take the square root of 4 and you have the 5 left over. You can do the same thing with letters. What about y to the 3rd? Can I take any y to the 4th out of y to the 3rd? No, there's not even any. So I'm just going to leave that as y to the 3rd. And then anything that worked out with the multiples of 4, I'm going to take it out. So what is the 4th root of x to the 4th? Just x. Anything that's less than 4, you can't take it out. Just like you can't take the square root of 2 or you can't take the square root of 3, you can leave that under the radical, and that's just going to be x squared y to the 3rd. What'd I forget? 4, I wrote it as a square root. Okay. And that's not very pretty, which is why the other thing that's in this section is using those rational exponents. Maybe is a better way to write it. But this is where we're going to stop today. Some vague memories of this from last year, Brandon. You're about to fall asleep on me. Not good. What is this? Cube root of 16. I do not want the decimal for a cube root of 16. I want you to simplify any perfect cubes that you can take out of that. And so that's where you have to be aware of cube numbers. Or if you aren't aware, just think about, start with 2. Usually a pretty small number. 2 third power is 8. Yes? Yes? Yes. So when I see 16, I know right away that I could take 2 to the third power out of that. And so I don't know how you guys did it in Algebra 2, but for me, when I break this up, I'm going to rewrite that as the cube root of 8, and then what times 8 gives me 16, I'm going to have a 2 left over. So Chase, do you have a shortcut on this? How do you do this? That doesn't help. I mean, I know how I do it. I was just wondering. Like your division thing. Because this one, it works out really nice that x cubed, right? 3 divided by 3, you can take the x out. But what about 8? Like, how do you do that without writing anything down? But he does usually do his homework, actually. So. He just doesn't take notes, and he likes to sleep in class. Those are Chase's faults in math class. But he did his homework most of the time last year. He did. He likes to pretend he doesn't.
I don't even pretend that. If I tell everybody that I do it, they just don't.
They don't believe you. So Chase is saying he says he knows he can take a 6 out of that, and then the 2's left over. So maybe he just does that in his head. Maybe you want to do it in your head. Maybe you want to just write out that 3, like how many y cubes are there. I don't know. Does anybody have any ways that they do this? I feel like sometimes I make it way more complicated than it needs to be by writing this all out. Right? Is that way too complicated? Because I'm making the 8 like I did this. Here's how I do it, honestly, but I always feel like that it's not showing enough work that you don't know where I'm getting it from. I always say, like if we do the dividing thing, 3 divided by 3 is 1. I say, how many times can I divide 3 into 8? And what's the answer there? 2. So I know I will be taking out a y squared. But then, like, what would my remainder be? If I remember the good old remainder days. If I divided 8 divided by 3, I could do it 2 times, and I'd have 2 left over. So that's how I know I have a y squared left over. Does that make any sense? That's how I do it. Because I always feel like I need to show this whole step here, but then people think that's complicated. So the same thing for z to the 4th. I would say how many times, if I took 4 divided by 3, how many could I divide into their whole? 1. So I'd have a z, but then what would my remainder be? 1. I'd have a z left over. I don't know what the best way to write it out is. Or you can say z to the 3rd with a z left over. Or you can just do it in your head. I'm okay with all of the above there. But you got to be able to think through it. Your book has a ton of examples and writing in here. Another good thing about trying to get you ready for college classes is look in your books and read some of those examples. Maybe go out and look for online. There's tons of online videos out there. If you feel like you have no clue what I'm saying, like search out other resources on how to do this. But if I was going to write my answer here, everything that's a perfect cube gets to come out. So the cube root of 8 is 2. It gets to come out. So that's gone now. Because the cube root of 8 is 2. I lost the cube root sign. The cube root of x cubed is x. So that's gone. The cube root of y to the 6th is y squared. And the cube root of z cubed is z. And then everything that wasn't a perfect cube has to go back under the radical sign. So I'm left with a 2, a y squared, and a z. The next time we're together, we're going to talk about rational exponents, which is the same kind of stuff, only instead of using radical signs, we're going to do like to the 2/3 power and the 1/5 power. But if you have to kind of understand this before you can do the other stuff, I think I had one more example, but we're almost out of time. Just real quick, we won't actually do this whole thing. What do you think will be a smart first step on this one? Okay, you can multiply these together first. This is just square roots. You can multiply square roots just like you can undo square roots. So the first thing that I would do is take 3 times 6, which is 18. And a squared and a to the 5th is a to the 7th. and b to the third, and b is b to the fourth. So then I only have to break that up, and hopefully maybe doing square roots are easier than doing cube roots and fourth roots. But you really have to kind of think through what makes that work. How can I undo that as you're doing these? Questions about that? All right, I'm going to give you the assignment for the rings here. We are going to spend 2 days on this, so this would be section 1, 2, day 1. Here's some nice things to know because we don't turn our homework in every day. Let's say yesterday's homework you didn't use very much paper. You're welcome to just kind of draw a line and then start this homework underneath it because you're going to turn it all in at once to me, so you don't have to start a brand new sheet of paper every time if you have a bunch of paper left over. So you just want to make sure I can see where one ends and another begins. So if you haven't had my class before, that's kind of something to know. Something else to know, I don't know if your other teachers have done this in the past, but this means every third problem. So 12 through 30 times 3, that's just me not wanting to write multiples of 3. That means you do like 12, 15, 18, 21, 24, 27, 30. Right? So you count by threes. I like that because every other one is odd, so you can check every other one in the back, and it kind of spreads out the problems. So 57 through 66 times 3, every third problem, and then 81 and 82. I'm hoping we'll have time tomorrow after the Ivy Tech application that we can at least go over this, and we might even take some more notes tomorrow. Try to remember to get your Social Security numbers for tomorrow as well. Look at your books.